my name, Franziska said, is Wolfgang Keck. I studied electrotechnics at the Technical University of Berlin. And then I joined the hospital in Berlin. And then I joined the Hochschule Ulm. That's a university, something like the university here for applied sciences. And there is a course, we have a course in medical engineering, a bachelor course and a master course. And there I'm teaching. Yeah? Okay. First of all, English is a foreign language for me as for you. Yeah? But we should try to understand. If it's too fast for you, you have to say. Yeah? If I too fast speaking English. And it's not really a lecture. I think we should try to discuss the topics. Yeah? So if you have any questions or something like that. Okay. I have prepared two things, and I start, and I think it will be enough, with the second part. That is the part of fall detection, a special topic of medical engineering or informatics, like you want. And okay, at first we should speak about the examination. Sometimes may be it's important. And my idea is the following. I have prepared I have with me some scientific papers, yes, about that topic concerning fall detection. And so 7 papers, I think, yeah. And you should give me in groups of 2 or 3 students, we can organize that, on Friday. That means this week on Friday, because that's my last day here in Madrid. A short oral presentation of the content of one of these papers. Yeah, you get a paper, you get another one. All these papers are concerned with this topic of fall detection, and 10 minutes or something like that as oral presentation here. And then, let me say, on the 1st of June, that is nearly little bit more than 1 month, you sent me by mail a written description of this paper, something like 2 or 3 pages. Yeah, no more. And then I can do the marks, and I will send it to Franziska. So far? So this week you have to work, because you have to read one of these papers, and you have to prepare an oral presentation. I simply want to force you to speak in English. That's the main idea. Yeah? Okay. And that's important. We do not record anything on Friday. Yeah? Okay. Good. Fall detection. That's not really a lecture. It's a research project in our lab. A research project just some kind of finish now. And I cannot give you a lecture about a ready existing solution, but it's more a report about the actual state we have. Yeah? Actual state of the development. Why is fall detection a rather important topic? You see some numbers here. Falls and fall-related injuries. 40% of people older than 75 years fall at least once a year. 40%. 60% of them fall again within 1 year. 80% of falls happen during all-day living movements from upright position. That means from standing position. 30% falls happen during the night. That's very important. And 3%, and that's especially in the night, lie more than 20 minutes after a fall waiting for help. Yeah. As the sources for these numbers are the report of the Kellogg International Work Group. Then there is a paper of Downton and Clemens Becker and Tinetti. And I have some numbers for Spain. That is, these numbers are for Great Britain and some numbers are from Germany. For Spain, I found nearly 15% of Spanish people older than 65 years old have suffered a fall in the last 12 months. 7% of Spanish people older than 65. Yeah? You see here 40% of people older than 75 years. And this number 15% older than 65 years. Women are more affected as men. The numbers here, you see, the risk of a fall rises with the age. That's okay, understandable. People who have fallen once have a high risk to fall again. Falls during the night, often going to the toilet without switching on the light, are very risky because they lie on the floor for a long time waiting for help. And then may happen hypothermia in the winter especially, or dehydration. In Germany, we have more than 500,000 medical treatments caused by falls. We estimate we have costs in the health system for consequences after falls of about 5 million euros per year. And even without severe injuries after a fall, many elderly people want to live in a nursing home after that experience of a fall because they are very afraid to fall again. That's the problem. Yeah. Okay. It's okay for you? What is a fall? That's not an elderly people here. It's a young woman. There's a definition that says, okay, a fall is be lying unintentional on the floor or on a lower located plane. Okay. First, obviously, a fall is a change of position. Yeah, from upright position to lying position, or from sitting position to lying. But even a fall may be you sit and in this way. Yeah, it's possible to get an injury within this movement, or in this way from a sitting position to the floor. That, I think, the change of the position or the orientation of the head or the body in the room, that is not very difficult to measure. We will see that, how to measure. The problem is the word unintentional. Unintentional means it happened. Because all of the day we have many intentional changes of position. If I'm standing and I want to sit in a chair, or I'm sitting and I want to go to bed. Of course, that's a change of orientation in the room. That are so-called all-day living movements. And that are no falls. Yeah. We will see what we'll do with the problem with the unintentional. Okay, now your part starts. Do you have any ideas to detect falls by means of technical instrumentation sensors, something like that. Any idea?
Maybe a mobile phone. A mobile phone.
Yep. Okay, but then you must be able to operate the phone. Yes. We will see that is on the market, something like that. Yeah. That is, the name is emergency call systems. They are commercial available. I think even in Spain, I think. It's a button. You have it here or on the wrist, and you can push the button. The problem is with these buttons, many people who fall are in panic and not able to push any button, or even unconscious. Yes, and then we have a problem. Okay, other ideas? Okay, yes. Video control or the video monitoring of the room, of a room. In USA, I know some papers concerning this idea. There are two problems. It's very expensive, the first one, and the second one, I don't know, do you want to be video controlled all over the day in your room? I think no. Yeah? So we have an ethical problem. You understand ethical? Yeah. And we have to consider such problems for techniques for elderly people. Yeah? Not anything which is technical possible is really a good idea for that people. Other ideas?
That means that measures the difference of position of the body and
Yep.
make a difference between the soft changes and the fast changes of position, perhaps.
Okay, maybe. Yes, there are some ideas in the direction of machine learning, the learning of individual movements in the normal day, and so the detection of faults may be possible. Yeah, but we have to measure, and then we have to distinguish between measurements in the room, that is with a camera, or with contact maps, something like that. Yeah, if something lying on the floor, you have a contact mat, you understand that? You can see the position or measure the position. That is room-oriented. And the other one is person-oriented. That means you measure on the person. Yes? Any part of the body. We will see some solutions of that. Stationary, we have motion detectors, we have contact mats, and we have possible video controlled monitoring. Video controlled monitoring is too expensive and ethically problematic. Contact mats, I think there is no real functional solution on the market. And motion detectors, maybe not the worthest idea, because they are very cheap. And some problems may be solved with these motion detectors. Body-worn solutions, that means you measure acceleration at the body. That can be on the chest, on the wrist, on the head, where you want. We will see, we do it on the head. You can use gyroscopes, you know that? That are sensors measuring the angular velocity. That's maybe a good idea. I'm not a friend of this kind of sensors, but okay, they are rather cheap today. But also accelerometer sensors also are very cheap. It's no problem to buy them. Well, and you can wear that on the hip, on the body, chest, like here, or on the head. We will see on the head. Some requirements for this kind of systems. Anyway, which sensors you take or where you measure. These are requirements for all such devices. First, we need a very good sensitivity. That means each fall should be detected as such. Yeah, that is the definition of sensitivity. That means every real fall should be detected as a fall. Then we have specificity. That's a big problem with alarming systems. That means no false alarms. That means any all-day living movements should not be detected as a fall. And false alarms, that's a big problem with any alarming system. Yeah? That's the specificity. There should be no risk of injury caused by the device itself, of course. Yeah? You cannot construct or develop a device which may cause injuries by itself. It should be wearable, comfortable during day and night. We have seen many of the falls happens during the night. So it must be possible to lie in a bed and wear the system. That's a problem with all the systems fixed on the hip. That's not comfortable. It should be easy to put on and easy to operate. And, well, for me, or for our idea, for my group, measurement should be at a part of the body with only small movements during all-day living movements. There are systems measuring on the wrist here. The problem is you move with the arms and you take something like that. May happen. So you have heavy movements here. But you have no heavy movements or fast movements normally with the head. Yeah? Okay, so measurement on the head may be a very good idea, I hope. Something about existing solutions, commercial available solutions. The first one, you told it, emergency call systems, like the left one here, that's a system manufactured by Tunstall. That's a system with a button. But additionally, in this way, yeah, this device, the left one, registers the position of the body in the room, but only the position. That's not really sufficient for the detection of falls. But all of these systems have an emergency call button, of course. Then we have in the mid, that's a system manufactured by Atendo. Yes, that's an Atendo device. It also detects changes of body position and is also fixed on the hip as the system at the left. Yeah? And at the right, that's a wrist-worn device. That comes from Vivago and registrates changes of trained positions. That means in this system, you have a set of learned movements of all-day living movements. And if there is a difference to these all-day living movements, the system says, okay, maybe a fall. But the problem is worn at the wrist. This place is as the advantage, you can wear it during the night. Yes, like a watch. The other one, it's not possible for the night. Fixed on the hip, yes? The people can't sleep with these devices. Okay, our system just now looks like that. You even see it here. We can play with that system today if we want, or tomorrow. First, our idea is we measure accelerations at the head. This is one beyond the ear. Yeah? And just now, at the actual state, we have a cable connected to this device. This device must not be worn on the hip. You can do here or something like that. Here is accumulator, battery, a microcontroller, and we will see a Bluetooth connection to the computer. Yeah? The advantages, we think our advantages, during all-day living movements, there should be only small accelerations at the head, measured here. The device itself, worn at the body here, is very small, and wearable at the head is comfortable for the people and suitable for measurements during the night. And we have seen big accelerations measured at the head are typically for severe falls. If you fall, it's rather typically that we have big accelerations during the impact, especially during the impact on the floor, accelerations on the head. We do not have normally with all-day living movements. The system until now, as a block diagram, you see acceleration sensors here. Beyond this red. And the microcontroller, the Bluetooth module, and the battery here, and the cable. And then a Bluetooth connection to any computer. I don't know, do you know anything about acceleration sensors? How do they work? No? You're studying informatics and not sensoric or electrotechnics? Okay, then we will discuss that very short. I think it's even important also for informatics. You see here, okay, first, where do we have or where do we use acceleration sensors in devices? Do you know any devices with acceleration sensors? No? Mobile phones, okay. The modern mobile phones have acceleration. Think on the iPhone. If you this movement, yeah, change of acceleration caused by the gravity of the Earth. Another one. Do you have a car? Huh?
The game machine, the remote control of the Nintendo Wii, for example.
Yes, okay. Or if you think on airbags in cars, yes, that are acceleration sensors, one part of these airbags. And if you think on a laptop, yes, there is a small acceleration sensor for the hard disk in every laptop today. Okay, so these accelerometers are very cheap today because it's microsystems, and you pay for this one 50 cents or something like that. And you see it here. That's the sensor mounted on a breakout board. We don't use this board here. And it's a capacitive sensor with two axes, X and Y axis, they say. You see here the X direction and the Y direction for the sensor, and an X, X and Y output of that system. The rest is ground and so on, power supply. That comes from Analog Devices. That's the manufacturer of this system. You see here the sensor with the two capacitors for the two directions. There is some amplification, a demodulation, and then an output amplifier for the X and for the Y and for the X. That's all. Power supply, ground. And some external capacitors here and here. Okay, how does such a sensor work? You see here a system that is just this part with these two plates here. That's the so-called seismic mass. And if there is a force in this direction, you can imagine this distance here diminishes, gets lower, and this distance here is enhanced. And maybe from school you remember the amount of a capacitor is dependent of this distance. Yeah? So if the distance changes, the capacitor changes. And that you can measure. In this way, we have two capacitors. This one is C1 and C2, and that's a seismic mass. You can imagine if you thrill it in this way, there is no external force. So there is no, both capacitors are the same. Yes, but in this way we have the gravitational force, and then this distance here is smaller than this one. Okay. And then you see the first capacitor is the rest capacitor plus the change, and that is minus the change. And the change is minus this change in the distance or plus change in the distance. And normally they are connected in a half bridge circuit. You see it here. There we know full bridge circuits and half bridge circuits with two fixed resistance and the two capacitors and the power supply here. And then the voltage you can measure here depends only on these changes of the capacitors. In this way, that the output voltage of such a half bridge is minus the power supply divided by 2 multiplied with the change of the capacitor divided by the rest capacitor. Okay, that's all. Our system here has a measurement range of plus minus 18 G. That means 18 times gravitational constant. Gravitation constant is 9.81 meters per second squared. Yeah? That's the measurement range here. The sensitivity of this sensor is 57 millivolts per G. The resolution so is 3 milli-G, and the frequency response is adjustable by means of the two capacitors you've seen here. That are the two capacitors. Between 0.5 and 2,500 cycles per second. And the equation for that is this value of C. And for our application, we decided that a frequency response of 100 cycles per second is enough. So these capacitors have a value of about 50 nanofarads. Rather small. For our experience, that's the minimum value you need. We know something of faults with values bigger than 18G. Yeah? So that's a minimum, we think. That's important because sometimes you read in the papers something from sensors about sensors with plus minus 2 or 5G. That's not enough. A little bit more would be fine, but it's not on the market. That's the problem. And there is another problem. Because unfortunately, this sensor here, you see it, that's the sensor here, and that's another one sensor here, has only 2 axes. There is no sensor with 3 axes on the market with this measurement range. You get acceleration meters 10G with 3 axes, but 10G is not enough. So we took 2 of them, mounted them rectangular on 2 boards. You see that here. These 2 boards are rectangular in this way. And we only use, so we have, of course, 4 sensors, but we use only 3. The one is not connected. And that is what you see here. That is that board. And in a mounted version, you see it here on the right. Yeah? The orientation of the 3 axes you see here, but sorry, there's a little mistake. Okay, Z positive goes to the ground. If I have this in this way, Z is positive in this way. Y is positive forward. And X is positive, you see it here to the left, that's wrong, it goes to the right. Yeah? And if you open this housing here, that system, okay, mainly you see the microcontroller here, that's a PIC from Microchip. That's a microcontroller we use in Ulm very frequently. That's the Bluetooth module here, and that's the battery. And the battery is good for 1 day until now. Okay, the job of this part I think is clear. Just measuring accelerations in 3 directions. Yes? What's the job of the microcontroller? It's not a job, until now, it's not a job of this controller to detect faults. But it just manages the measurement. The real detection, the final detection of a fault is here on the computer, until now. Okay, but what is the job of that microcontroller? Let's have a look to a fall. But that's an intentional fall of a young woman backwards. And you see a gymnastic mat here, because of course we don't want any injuries during these experiments. And I think you believe me, nobody falls in this way. normally. Yes? Because normally you go in this position. If you feel, oh, it goes back. And here, and that I can demonstrate better with the software we use. You see the acceleration signals in green and blue and red. And red, that is, yes, you cannot see it in your papers. Sorry, but it's not possible to do color copies. Red, that is the x direction. Blue, here, that's the y direction. And green, that's the z direction. And you see here the black line, that means that is the trigger point. There was the measurement triggered. Normally, we measure some data, but if there is no trigger, we have no suspect that there is a fall. Yeah? You see the time from 0 to 2.56 seconds. That's the duration of our measurement. And you see here in the y-axis 8g to minus 8g. That's in a zoom situation here. Normally we have plus minus 18 or 20, yeah, 18g. Okay, let me show that on a program. I think it's better. That are recorded movements. It was that one, yeah. Okay, we take the same zoom. Then we have the situation just like before. And you see here, that is x, the red one, y, and z. And here you see the sum of these three signals. The sum means always it's all values in x, y, and z directions squared, summed, and then the square root of that. Yes, because we have x, y, z component. That's a three-dimensional vector. And if you want to compute the amount or the sum of this vector, the length of the vector, you have to sum the squares. You know it, I think, from mathematics. Or yeah. Note here, you see the values if I move with the mouse here. Yeah? You don't need that. Here we have nearly 1g, 0.92. That means the person is not moving very fast, but the sum of all accelerations is just nearly the gravitational constant. Okay. Then it gets lower. You see here, we go down, we go down, we go down, we are here, and there we have 0.2. That's the fall phase. If there would be a value of 0, then we have a so-called physics, some remembers, memories, free fall. We call that a free fall. Yes? If I take this one, that's a free fall. There's 0g on this. Then here, that's the impact of the movement. Yeah? And then, okay, the person is lying here. Okay, we can have a look first here for the position. Can we say anything about the position? You see the values of, I hope, yeah. You see here the values here for the x, y, and z direction at this point here. There we have a set of 0.8. That means we have rather upright position. The head a little bit flexed to the front. That are the 0.4 in y direction. Remember, this was plus in y direction. And a little bit flexed to the right. That maybe the person is standing, head in this way and this way. Yeah? So, that is important. We can registrate the orientation of the head in the room. With these values we can say, okay, the head, not the body, but the head is in this position. Upright, a little bit flexed forward to the right. And after the fall, here, let's have a look. We have minus 0.8 in y direction. That means the person must be lying on the back. Yeah? The head a little bit flexed forward, that's the Z direction, the 0.4 you see, and a little bit to the left. That may be in this way, lying on the back. So we can say, okay, there was a change in position from the beginning of the movement to the end of the movement. But for that, we have to know where is the beginning of the movement and where does the movement stop. That's a problem. That here is not really important, but this point is important and this point is important. Because before this time, and that is before our trigger point, we have the information about the orientation of the head before the movement. And if the motion stops here, something like there, we have here an information about the position after the movement. And so we can see, is there a change in orientation? Maybe it helps in this way. That's a pseudo three-dimensional presentation. We will see it for some other cases. I zoom it a little bit. That's the situation at the beginning. Yes, it's very stable. You see here. That's the Z direction. You see we have 0.8. That's the Y direction and the X direction. And the three axes, Y axis, X axis and Z axis. Okay, and if we look at the end, we have this direction. X, Y, minus, lying on the back, and a little bit Z down. And if you look for the resultant vector here, you see it in this way. Any questions so far? No? The tempo is all right for you? It's understandable? Okay. So our strategy for the detection of falls was first detect the orientation of the head before the movement. We have just seen before. Yeah? Can go back. We take this here, this information here, and say, okay, that's the position of the head before. Then we have to detect the beginning and the end of the movement. Then we should be able to detect the orientation of the head after the movement. And then we can judge if the movement is like something like an all-day living movement or a fall. Yeah? That means a fall is defined for us. First, it's a change in position between before the movement and after the movement. And then we have judged the movement itself. Maybe it's a fall, or maybe it's an all-day living movement. And so we need the beginning and the end of the movement phase. Maybe a fall phase, but it may be also an all-day living moving phase. And, well, one need for that strategy is we need acceleration data before the movement. And that's a problem. Remember, we have a system with the 3 sensors. And we have a microcontroller. The microcontroller simply may be constructed in this way, that we say, okay, if the acceleration exceeds some threshold value, we start with measurement. But then we have the problem, there is no data before the trigger point. You understand? Okay. How we can get some data before the trigger point? I want to look beyond that point. It's very easy to detect some threshold in acceleration. That's no problem. But we need the data before. Well, that's a classical informatic problem. You ever heard something about a ring buffer? Yes? Okay, that's the solution. You can do it by means of a ring buffer, of course. You see here, the microcontroller samples the 3 acceleration signals continuously in such a ring buffer. Well, that's only a simulation of the real program of that microcontroller. Oh, we stopped that program. Yes. We need it later on. But we start. You see, that is what the microcontroller does. If I switch on the microcontroller with this red knob, I do it just now, not because I need the battery until Friday, maybe. Then it runs and runs and runs. Endless. Yes? That means it measures the 3 signals, you see only one, the 3 signals of the acceleration sensors in X, Y, and Z direction. And if the trigger condition is met, and the trigger condition I will say later what it is, then it stops. Yeah? And now we can say the data before the movement is here. That was the trigger point here. Yeah? That is acceleration after the movement, and that is also acceleration after the movement. And now I simply have to shift the signal so that this point here becomes here, and this data here must be here. And that runs like you want. We start again and take another time for the triggering. We take it here. And the measurement now stops. And the shift is very simple, because we say, okay, that is closing the ring, and that is the start of the movement. That means that is 0 seconds. Okay, so the shift is very easy. That's the shift. Yeah, it's just shifted this way, and then we can mark. Okay, that is one step. Another one. Okay. Yeah. Some technical data. You see here that are slides you have it in your papers, but it's the same you've seen with the program. Okay, we decided to sample with a frequency of 200 cycles per second. Do you know anything about the so-called sampling frequency theorem or sampling theorem? You ever heard something? What does it say?
Set off 2 times of the main.
The highest frequency. Yeah, the highest. You have a signal, and you have to estimate. Okay, what is the highest frequency in the signal? We said, okay, it's 100 cycles per second. We have chosen the capacitors, you remember it? In this way. You said, okay, there is a low pass, stops at 100 cycles per second, so we have no frequencies more than. And then a sampling frequency of 200 cycles per second is okay. It's just 400 may be better, but 200 is okay. Okay. The resolution, that means the analog digital conversion, is 10-bit. It's better than 8-bit, we decided. First we had trial with 8-bit, it's not enough. Our ring buffer now, exactly, that are 3 ring buffers for the 3 signals, have 576 points. And so we have a duration of the signal before the trigger, that means data before the movement, of nearly 1 second. And after the trigger we have another one, nearly 2 seconds. So overall we have a duration of nearly 2, yes, in the new version nearly 3 seconds. In the versions of the slides here, we have 2.5 seconds. Okay, what is the actual trigger condition? Remember the signal here. I triggered it with a button, yeah. This way. Oops, that's wrong. No, it's okay. Good. The actual trigger condition you see here is a change of acceleration in one of the three signals of more than 2g, 2 times gravitational force, in an interval of 15 milliseconds. We sample with 200 cycles per second. So we have a sampling interval of 200 cycles per second is a sampling interval of 5 milliseconds. Yes, 1 divided by 200. 5 milliseconds, and then we have a difference between three sampling values. That are these 15 milliseconds, and there a change more than 2g. Then we say, okay, that was a trigger. I can try to demonstrate this. What happens? Comes. I have to install a Bluetooth connection. I hope it runs. It runs with COM6. Okay, thank you. Stop this probe. Close. Now the microcontroller runs and runs and runs with this ring buffer. You see nothing on that program, yeah? But now we simulate a sudden movement. I hope it's sudden. Was sudden, no? No. Oh. Yes, I see. It's wrong. It's a wrong COM. To go there. That is okay. That's here. But no data. Very strange. Something happened during the flight. I have the connection. Not fine. Let's write COM. There is a trigger, but no data. Well, I have to try what happened there till tomorrow. There are constant values, there is no change. Sorry. We will see. Switch off. Maybe. Okay. Searching for the beginning and the end of the movement. That is necessary because we need an information. Where is the situation before the movement? And where is for registration of the position? And where is the situation after the movement? Fixed is only this point here, the trigger point. That we know. Yeah? And then we have to look what happened before, what happened after. And here you see, okay, we have said that's the beginning of the movement. Why ever, we will see. And that's the end of the movement. We will see why. What is the criterion for that decision? We can try to visualize that in our simulation. Here. The trigger. We shift. And then we can try. Oh, it says that is the start and that is the end. Fine, but why? The decision made is in this way. You see here, you don't see here, really. The mean value and the standard deviation for an interval of 50 values. Yeah, that are the first 50, the second 50, and so on. It's very constant, you see, and now. You see? Especially you see the standard deviation gets bigger. The mean value, okay, that's not really important at that point, but the standard deviation. And is here, and is here, and is here, is here, and is here. There we are low in the standard deviation. And what you see also, for a better resolution in time, we decided that if this is one interval here in the length, they overlap with 50%. That means we start with a new interval every 25 values. Overlapping intervals. You understand that? It's simply to enhance the time resolution, because otherwise we have this one from here to here and the next one starting here to here and no overlap. that's a trick. You can overlap 50%, you can overlap 25%, you can overlap 75%. It's a question of computational resources you have. Yeah? Because of course, overlapping means you have more to compute. And you need a little bit more memory. But that's no problem here. So you see this here again. We subdivide each of the 3 acceleration signals in intervals. Each interval contains 50 sampling points. So each interval is 0.25 seconds long, of course. And for a better resolution of time, the intervals overlap with 50%. All of over the time of our registration time, so in this way we have 22 intervals. Remember the 2.56 seconds of duration of the signal? Then we have 22 intervals. And I think the equations for the computation of the mean value and the standard deviation, I think you know it. You have seen it. I don't know where, but I hope you have seen it anywhere. For the mean value, just simple sample at all sample values and divide by the number of values. Yeah? So you see the sum divided by 50. And okay, for the standard deviation, maybe you know 2 different equations. That's the more simple equation, but the difference is very small, and this one is simpler to compute than the other one. You need the mean, and you can do it in one loop. You add the sample values itself for the mean, for the computation of the mean, and you add the squared sample values, because you need the squared sample values for your standard deviation. That's the sum here. This one is the squared. You have to square the values and then to sum up. Yeah? Okay, at the end of your loop, that means 50, you just compute the mean, dividing the sum by 50, and square it, this mean value, and subtract it from this, and then compute the square root of that, and you have the standard deviation. Computing the square root is no problem on a PC. It's a problem on the microcontroller because it needs time. It's a problem of scaling. You can also say, okay, we don't compute the standard deviation, but we compute the without the square root. What's that? Do you know anything about statistics? Yes? Okay, then you should know it. What is it without square root? Yeah.
The
Variance. Yes, it's the variance of the signal.
I don't know the name
in English. Varianza. Okay. No, I know it in Spanish. Okay. And I hope you know, if you have big changes in a signal, you have a big variance. And if there are only small changes, you have a very slow variance. So the variance is a really good measure for the activity in a signal. If you have anything to do with signal processing, measuring of noise or something like that, if there's big noise, you have a big variance. If they're low noise, you have a small variance. Yeah, and that's the trick here. It's the same way. In the simulation, okay, you have seen it just before, and you see again the overlapping here, and you get a very small threshold value. We say the beginning of the movement, is defined if the standard deviation in the samples before the movement in one of the three signals is more than 0.1. Yeah, that's a very small threshold value, but it's very suited. You see it here. Here the standard deviation is less than 0.1. And for this interval here, the overlapping interval here, starting here, it's more than 0.1. The same we do at the end. We say if it's again less than 0.1, we say, okay, that was the motion. The motion stopped. And the rest of the signal is only interesting for registration of the position. You see that here, the same. Okay, we can have a look to our program. You don't need that. That's the data just before. You have seen before that's the intentional falls backward. Yeah. And now we don't want to see that, we don't want to see that, don't want to see that, and don't want to see that, and don't want to see that. Now you see nothing. Now you see the mean values. Not, it's confusing if I show it overlapping here. Yeah, but in fact, the next interval, this interval goes up to there in the overlapping manner. Yeah, and then you see here, I don't know in which signal we have the exceed of 0.1 in the standard deviation. You see the mean value and plus minus standard deviation here. We have to look in which channel it is, because we check the three signals for this start and end. Okay, in Y you see it, the beginning. We can see here in Y, you see on the right here the mean value and the standard deviation. Yeah, the mean value and the standard deviation. And here, okay, it's more than 0.1. At this point, in X, no. You see, no. And in Z, I don't know. At this point, yes, also in Z. Here is less in all the three signals, less than 0.1. And here it's more than 0.1 in Y and Z direction. Okay, it's more, it's more, it's more, it's more, it's more. We are here. Okay, it's less than 0.1. and here in both in the three signals, more than. Okay. So you see the criterion for this line, that means the end of the motion, and this line, that means the start of the motion. Yeah? You don't see it in this way, but that's the computation in the background to find the beginning and the end. That is, this line is our trigger point, that's fixed. Because we know, okay, so much data before the movement, and the ring buffer, the position of the trigger point in the ring buffer depicts the number of values before the movement. But the actual start of the movement, we have to decide by means of the standard deviation, and also the end of the movement. You see the same here. And for that case, okay, you see the position, we have seen that at the beginning today. I hope you remember that. Well, you see it here in the x and y plane. The angel here of this line here is about 60 degrees. I hope you believe it. Yeah? And if you look after the movement here, and we compute the angel in this way, in the positive direction, that are more than 180, that is 254 degrees after the movement here. Yes, okay, we've seen. From here to here is 180. To here would be 270. Yeah? So here we have 254. Okay. Let me go so far. Another example. I can just try to demonstrate that with the program. Better. Go back. Data. This one. This one. Read data. This old one, okay. So, that's not the first measurement. This one. Okay. What's happened here? You see, start of the movement. There is a movement. Trigger point, end of the movement. We have a position here. We have a position here. Do you see something? Look for these three signals here and the three signals here. It's the same. There is no change in position. Yes? I don't know what happened there. We can have a look. Strange is the following. In y, in 0, we have, in z direction, we have nearly 0. You see here, yes? My mouse is where? Poof. Here. 0 in z direction. Minus 8t in y direction and minus 0.6 in x direction. What position is that? It's on the back to the left. Yeah, there is no z. If you think on that, z this one, y this one, x this one. It must be in this way, to the left, in this way. Yeah? And now think, okay, on the ear, it must be something like that. Maybe there lies somebody in the bed. We don't know it. Because that are measurements in a nursing home, and there was not always somebody present in that time, during that time. Because the people wear this system 24 hours per day, and we don't know what do they all the day, during all the day. Yeah. So we say it could not be a fall, because whatever happened here, it's a lying position before and it's a lying position after. Then we should have a change in the position. It's very, no, I don't think so. Yeah, then you go on the front or to the side. Yeah, I think maybe somebody shaking a little bit with the head, lying on the back this way, maybe. It's not very because we have only in this, normally we see it in this way. 18, do you see here the measurement range of 18 plus minus 18G? Yeah, and then that is rather small, these values here. And we can also look for the movement at the beginning, that is this one. Yes, you see here, 0, as Z is 0, minus 0.6, and minus 0.8. And if we look for that, that's the resultant in the xy plane. And then we look after the movement, it's just the same. Yeah. During the movement, of course, you see, well, here. There happened something. Yeah. Strange things. Now it runs automatically for these 2 seconds. There's the movement. And then very quiet. another example you have in your paper. And then number 15. Yes. Some zoom. Okay, that should be the last thing today because we have to discuss something else. What do we see here? Here at the beginning you see the values for the x, y and z direction. You see some movement. The movement starts here, the program says. Maybe it starts here. And you see here there is a change in position. But was it a fall? I don't think so. Because here, that is too small. There are no big signals. We can look for that. Very small. Okay, and I think that should be something for tomorrow. That would be the second part of this lecture, and then I think we are here, yes, that runs. And then we have on Thursday time for the third part, that's fine. The next step we need. You see this one? That is our last example. That is the same example, this one, in this three-dimensional way. You see there is a change in orientation, obviously. And then for tomorrow, the last step we have is what is our strategy for the detection. If we have a change of orientation before and after the movement, that's wrong. We have to decide whether it is a so-called all-day living movement or a fall. Because that is really important for, remember it, specificity and sensitivity. Yeah, if you remember statistics, that are two words in statistics, sensitivity and specificity. Detect all real falls as false and detect no all the living movements as fall. That means no false alarms. That's really critical. And so we should discuss that for tomorrow.